All right, so now that we've talked about epsilon in terms of delta and using that to find a more precise limit, let's break it down on a graph so that we can actually see what's happening. So in this graph that I've drawn here, we have the y-axis represented by epsilon, and we have the x-axis represented by delta. We also have, just so we have a refresher from last time, the expression for a limit, which is the limit of f of x equals whatever the limit is, L, as x approaches a. So that just means anything that can be plugged in to the x value here, that's going to give us some coordinate x and y over here. This is what we're looking for. We're looking for this point. Now, this could be any kind of a function. Okay, so we've got our a. A is on the x-axis. That's the value of x that gives us our limit. And then we've got y. So at x equals whatever this is, we've got some value of y, which is our limit. And so really what this is saying, when we're thinking in terms of epsilon and delta, or at least the way that we were thinking of before whenever we set an arbitrary value in our set it up in our inequality, so we're essentially saying that this value here is going to be, so we set up an arbitrary value here of delta, well, a plus delta. So that would represent this arbitrary value here. And we set up another arbitrary value that's smaller than this value. And that can be represented as a minus delta. Here's the reason why this is accurate to what we're doing. These values are increasing from 0. From this point over here, which is 0, we're going outwards into infinity along the x-axis. And so the point being is that if delta is what represents our x-axis, well, then this can be represented, since it's a quantity that's bigger than a, as whatever value of x we have here plus delta, whereas this one can be represented as something that's smaller than a, so a minus delta. And we can actually do the same thing for our limit. And so we can say, so we add this guy right here, and that is now L plus epsilon. And we can add another one at the bottom down here, and we can say that this arbitrary value is L minus epsilon. And so what we're essentially saying is that these two values are placed around whatever our limit is, such that we can get a more precise or defined answer for what this limit actually is. That is why we use epsilon delta. Now, this is what I think is kind of interesting about this, because this is where it kind of goes to show that limits are a definition for a derivative, and how it sets us up for understanding the complexities of a derivative, how you would derive an answer from a derivative without first being shown the shortcuts. So this is the meat of the math. And so if you look at this, so that what we're essentially saying here is what we said in the last one. So we're saying that some function, f of x, plus or minus, depending on what this term is here, if this is plus or minus on the limit, if it's a negative or a positive value, when it goes over to the other side, that'll determine whether it's a plus or minus on the other side. So whether it's added or subtracted from f of x. On the other hand, we've got down here x approaching the limit, which is how we get our delta. And depending on if this value of a here is a negative or positive quantity, the same thing happens. Whenever we translate it over, if it's a negative, well, then it becomes a positive. If it's a positive, then it becomes a negative. And so that's why I have the plus and minus here to represent that. Doesn't this, however, look eerily similar to the function f of x minus f of a over x minus a? Doesn't that look eerily similar? And couldn't that mean then that we can say that f of x minus f of a over x minus a is equal then to epsilon over delta, which then, because we find that this is essentially, we're looking for slopes now. We're looking for slopes at specific areas. This is a slope function, which is what a derivative is. So we can essentially then say that epsilon delta is actually equal then to, well, what's another way of finding a more precise limit? Well, it can be represented, and it's a much bigger looking function. It seems crazier than this function here, but it's essentially the same thing. But we do it when we're trying to find a more precise quantity of a limit. F of x plus h minus f of x over h. These two functions are the same. So we can say that all of these are equal to each other. So then what can we say from there? If this is really just setting up, if this is really just setting up our understanding of a derivative, then we could really just say that this is equal to d over dx, which is a representation of a derivative, or f prime of x, or, because it's also a slope, y2 minus y1 over x2 minus x1. And that'll do it for this one. Thanks.